This is it, the beginning to the rest of your life. I am very excited for you. This is an introduction to A-level calculus. Specifically, in this video, differentiation. Now, in this video, I'm not going to explain the fundamental principles behind why this works, because that is actually its own sub-chapter called Differentiation from First Principles. But for now, all we need to know is how to carry out the process of differentiation. Okay, first of all, what is differentiation actually? Well, before, I'm sure you've found many gradients of many lines, and what you would do is that you would take 2 points on the line and you would find the difference in the y and x and basically try and figure out what's the kind of like rate at which the x goes across for every amount that y goes up. So it would look like a kind of step ladder like this, and you're trying to see what is that rate of change. The exact same process applies to differentiation. The same idea carries over here. What we're doing is we take some graph, and in fact you can do this with a linear graph, but instead of taking 2 points like this, all we're doing conceptually is that we're bringing these points closer, a bit closer together, and then a bit closer together again, and then a bit closer together again, until they are almost exactly in the same position. And at this point, we're asking the question of, very specifically, at this point here, what is the gradient or the rate of change of this function? That is where differentiation comes into it. Now, the actual method that you can simply memorize for A-level purposes, let's say you have some constant x to the power of another constant. To differentiate this is the notation we use. And by differentiating this, what we're doing is we are taking this exponent here and we're bringing it here, we're multiplying these two, and then only then afterwards we subtract 1 from b. So in practice that will look like this becomes a times b, lots of x, to the power of b minus 1. That's it. That's all that it comes down to. That is differentiation right there, summarized in that one line. Let's say we had a linear graph like we had before, so just so I can put this into perspective for you. Let's just say this is y equals 2x plus 3. Now, we know from GCSE quite simply that linear graphs are written in this form, so we can really quickly just look at this graph and say, well, there is the gradient. But notice how the same method I just showed you actually applies here, where we have 2x to the power of 1. The gradient here, if we said d on dx, 2x to the 1, is actually simply just 2 times 1 times x to the 0, which is just 2. So you see how the same principle actually still applies here. Let's go for... Now, the problem with identifying the gradient of quadratic is that, well, the gradient is changing at every point. Look, if we took a point here and we found the gradient, well, it would be 0. And at this point here, right next to it, it would kind of slightly start to go up like that. This point here, it would go up, but more rapidly. And if we go backwards this way, it actually starts to go down. And here, it's going down, and it's even steeper. So what is the gradient of this quadratic? right? We have no idea. And this is again where the idea of differentiation comes in. So instead of finding a specific gradient like we did with this example with the linear graph, we instead say that there is some function. There is some function, just like there's y equals x squared, there is some function that when we plug in the corresponding x coordinate, we will always get the exact gradient at that point. So to find that function, we differentiate the original quadratic. So d over dx of x squared. Same trick as before, we take this 2, we move it there, and then we subtract 1 from it. This becomes 2x to the power of 1. And notice how I've written d over dx, lots of x squared here, but we actually also know that y simply is x squared, so we can even write this like this, and this is how you'll often see it written, dy over dx equals 2x. And now this function here, this 2x, essentially is giving us the tangent at any point for this x value here. So if we had the x is 1, which would be somewhere here, let's say, x1, we have this tangent right here, and that would give us some gradient. Well, we know that the gradient equals 2, because it's just 2 lots of 1, right? Okay, so now let's get into an actual exam example straight away, and just see what I mean here. So the curve has the equation, blah, 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 blah. Find dy dx. This is how they often ask it, but remember what we said is finding dy dx is simply just finding the rate at which this function is changing at any given point. So in this case, well, y equals 2 over 3x cubed minus 7 over 2x squared minus 4x plus 5. dy over dx, the same trick, nothing changes. We have 3 times 2/3 makes 2 over 3 times 3, x, 3 minus 1 is 2, minus 7 over 2 times 2 gives us 7, x to the x to the 1, minus 4x to the 0. And now here we have a constant. So whenever we have a constant like this, this simply becomes nothing. We can just ignore it. And there we have our answer. Okay, now question 4. Another example here, same kind of principle. If you want, you can pause this video and give this a go, and then I will go through it and you can cross-reference your answers with mine. So dy dx is equal to 20x cubed minus, let's see, 24, 48, add them together, that's carry the 2, 172. 72x squared plus 84x minus 32. Okay, and now we have some new notation. Don't be frightened by this. It's literally the same thing. It just looks a bit scary. All this 2 means is that we take this dy dx and we just do it again. So instead of differentiating the original function y, we're now differentiating the differentiated function of dy dx itself, so this right here. So we just pretend this is the original function and then we differentiate that. So again, you can pause the video and give this a go, but 60x squared minus 144x plus 84. One more example for you to try, and the reason I've selected this one is because we're again switching up the notation slightly. Questions very well could be written out like this. and you just need to prepare yourself for what this means. It's exactly the same concept and principles. The only difference is that instead of y equals something, we're just given the function. So you can think of this y and f of x being interchangeable, essentially. It really doesn't matter. Now that we know that those are interchangeable, well, the only piece of information I even need to tell you is that instead of dy dx, to differentiate y, that's how we write it. To differentiate f of x, the function of x, we simply write it like this. F dash x. And that's the only difference. What that means is that f double dash x is just correspondent to d squared y over dx squared. And this could go for anything. You could have f triple dash, f quadruple dash. At some point they just start using numbers like this. You know, maybe f8 if you're doing some crazy stuff like that. But that is the only difference there. And that's all you need to know. So give this question a go now. I'm going to go through it quickly here. So f of x equals 3x cubed plus 4x minus 8. Therefore f dash x, or double dash x, sorry, is 6x plus 4. Again, don't worry about part B. I will cover that in a later video. But for now, you have just learned the very basics of A-level calculus. This is the first step on a very long road, and once you master this, you will be unstoppable.